So I want to go now to Ken Griggs, who has joined us, and I've been getting emails about Ken. So let me read you his bio first. Ken Griggs has a Bachelor's of Science and Engineering degree in Aerospace and Mechanical Engineering with a minor in Theoretical Physics from Princeton University, as well as an MS in Theoretical Physics from the University of Maryland. He's worked for the DoD as a software engineer through GE Aerospace and has career experience with Martin-Marrietta and Lockheed-Martin. He's also the founder of Imagine Studios and has recently joined up with our very own Jeremy Rys to create Hover Brothers in 2018. There we go. Thank you for joining us, sir. Thank you very much. And let me hand it over to you.
Okay, this is my first time doing this on Zoom, so
okay.
I apologize for any technical difficulties.
Well, and you don't need the mask on Zoom, but you.
Well, no. To appreciate the time in which we're living, in particular, you know, look, if we went back to where Newton did his work, he went home because of a pandemic.
Wow.
So we just kind of want to be reminded in the future when we look back at this time, what was really kind of happening, even if people don't believe it. But, you know, so I just want to, you know, just as a mark of history, that's all.
Well, thank you again
I'm protecting all of me from me. How about that?
Thank you again for joining us. I've gotten, I think, 5 or 6, maybe even 7 emails from people who are just super excited. They're like, "Ken's coming on to speak. That's awesome." So thank you.
That's very special. I really appreciate that. So let me just also make sure that I can get the presentation working well enough. We'll be sharing screens, obviously. So again, really my first time. Can you see my screen, or have I shared it appropriately?
I don't think you've shared. So it's still focused on you. So try clicking. There should be a green share screen button down there at the bottom of your Zoom.
It. There we go. Somewhere down there. There we go. Okay.
There we go.
Better?
Yeah. Oh, perfect.
Okay. Fantastic. So I don't really know what you guys are actually seeing, but I hope it's the right thing. Okay.
Yeah, no, that looks great. So let me mute myself out and again, just take it away, sir. And thank you yet again.
Well, thank you guys for having me. My name is Ken Griggs, and I created a theory called Project PhOENIX. And what we're going to be doing today is just kind of walking through scattering theory in quantum physics and in relativity theory, but scattering theory overall through the lens of PhOENIX. So the question that everybody, I guess, should be asking is what is PhOENIX? And in short, PhOENIX stands for the physics of entanglement, networks, and information exchanges. And basically, the central question, of course, that we're asking is, can we wrap all of everything we've ever known about anything in the universe up? That's a huge question, obviously. But that's what we do in foundational theoretical physics, as you guys are very well aware of. The essence of how PhOENIX approaches this is to drop down and dirty into asking some of the simplest questions, like, what is a measurement? Now, all of science is based on that question. Science is, and exclusively, only about measurement. So the central theme of what we'll be talking about today is exactly that. What I've listed here are some of the informal definitions of PhOENIX, like everything in the universe necessarily needs everything else in the universe in order to exist. That's a nice idea. What does it mean? That measurement is nothing more than counting patterns. That's a huge idea. But what does that mean? Or that the measurable universe is really a way of talking about the flow along a well or fully connected network. And again, what does that mean? All of these things have relevance. One of them has relevance to math. One of them has relevance to all of our experimentation. And another one has relevance to algorithms in computer science. So, you know, can we tie all of these things together under one very nice structure? And that's what we'll be talking about today. Oh, by the way, if you guys have any questions, I've got certain moments in the presentation. I could just call them random commercials. But really what they're meant to serve as is for you guys to go, hey, stop, tell me something more about this. I also have a slide number up on the upper, I guess, right-hand corner of the screen. It's a, kind of a strange gold. So, mark the slide if you're not, if you really want to get back to that one. You guys have probably seen this particular slide. And what we do here is to basically turn particle physics into effectively Lego pieces. And what we establish, and we're going to get into this only loosely today, but I wanted to mention that all of this is actually tied to exactly what we mean by scattering theory. So here you're just looking at what those pieces are that we talked about basically back in 2012, 2016, 2018, if you ever see any of my past videos. But these are quarks and leptons. But we're going to get through this because we'll deal with this. So formally, what the heck is PhOENIX? And formally, I mean, all of y'all can read. So the essence is that you'll be able to read this into the future. So I don't just want to read the words on the PowerPoint. But nevertheless, PhOENIX is again, a principle, a method for constructing all of the parts of physics that we already know, and then using those parts of physics in order to construct things in physics that we don't know. So for example, quantum gravity. That was something that we were able to achieve back in 2012, but we've just been building up on that. How far do you go beyond quantum gravity? For example, warp drive. So warp drive exists. We're not going to be talking about that today. That's the next lecture. But here we just have to establish the actual background. How do you understand what we're going to be talking about later on? Okay. So beyond the formality, let's get into what the heck do we mean by measurement. Okay, and this is a critical thing. I mean, when we're asking the question about science, when we're doing anything dealing with theoretical physics, if you can't answer this question, where are we really? So quantum mechanics has worked very long and hard through the years in order to try to establish what do they mean by measurement. Einstein was fairly certain what he meant by measurement, but as it stands today, it's still a question. So the best way for us to describe this concept, and if you can contradict it, I always welcome anybody to find a contradiction in anything I'm saying, or a counterexample contradiction. So the question is, what do we mean by measurement? And all we've ever meant, from as far as I can tell, is all we've ever meant by measurement is just counting structures. What is a structure? A structure is anything that's different from something else, right? So anything that can be established as, it could be a word, it could be an alphabet structure, it could be, an actual physical structure illuminated by gravity or by light, it doesn't matter, as long as it's a distinct pattern. And that distinct pattern can be counted. This is what we mean by measurement. The question then becomes, how do we make that relevant in terms of a mathematical underpinning? And so what we're engaged with here is demonstrating that quantum field theory easily comes out of the question of what do we mean by measurement? Now, the main principle when you're asking this kind of a question is something that has generally been called general covariance. So in Einstein's general theory of relativity, general covariance is the principle that underlies everything. And effectively what it says is that, and by the way, this is in a prior paper that we produced about 3 years ago on relativity theory in PhOENIX. And in that paper, we described the same set of things we're describing here for scattering theory. But nevertheless, general covariance is really a nice way of saying that the universe that we live in doesn't really ask, how are you labeling things? By virtue of however you choose to label them, the underlying physics should be the same. So the principle of general covariance is our mathematical way of framing that. Okay, so what we find is that in the language of things not having, what do we call them, labels, or making how we do physics label free, there is a concept in mathematics deeply devoted to that, and we call those permutations. So general covariance that we can demonstrate is actually another way of saying permutations. And then the question is, what the heck do you mean by permutations? Well, then we have a mathematical structure that we can turn to. And the best one that we found is called combinatorics. And a good reference that we use all throughout this particular presentation are two mathematicians / computer scientists who devised something called analytic combinatorics back in the 1970s and 80s and 90s. And one of them has recently passed. His name was Bachelor. And the other one used to be a computer scientist. He actually started the computer science department at Princeton. And his name is Sedgwick. But I've put references to their work at the bottom of most of these pages. Okay, so the main item that we deal with in permutations, in combinatorics, is something called generating functions. And let's just be perfectly clear about it. A generating function is a simple data counting device. It's nothing more than a spreadsheet, right, where you mark something, some pattern, and then you put a count on it. And the way you assemble the patterns and a count, we call it a generating function, is nothing more than a polynomial. So z squared, z cubed, z to the fourth, all of those things are basically different patterns. And then the numbers in front of those z squared, z cubed, z to the fourth would be the count of those patterns. So when you formally see what a generating function looks like, it looks like a polynomial. It's just got z and some variable, which is a way of accounting for some type of pattern. What do we mean by pattern? Z could represent red. Z squared could represent blue. Z cubed could represent green. We don't care what you mean, what you're assigning to the z squared, z cubed. It's just that they have to be distinct things. Could be oranges, apples, and bananas. And then the number in front of that would simply be the number of oranges, apples, and bananas. But when you look at it, you see a polynomial. And you're like, okay, that's just a polynomial. Well, that's good. It's a simple mathematical device that we're now using in order to count things. You determine what those things are. Okay, so that's what we mean by generating function. It's nothing more than a polynomial with integer coefficients, okay? So what we can establish here is that there's a specific type of polynomial. And this type of polynomial, we're going to call a cyclic generating function. Now, I'm kind of praying that everybody is kind of okay with math. You're not so bad with algebra. You're not so bad with matrices. So I'm depending on that kind of a level of proficiency. But if you have any questions, don't hesitate. So what we have here are statements about how a generating function can very simply look as the sum of z squared, z cubed, etc. And then what we recognize is that this cycle, this cyclic generating function, this very easy polynomial, if you exponentiate the whole darn thing, you get something even more substantial. It's called the permutation generating function. And that permutation generating function, and by the way, I'm in Las Vegas right now. The only reason why casinos work, the only reason why people make money on casinos is because of the permutation generating function. It tells the casino veritably how much they need to invest in order to get this machine to produce money back for them. So this tool, this permutation generating function, is your mathematical card counting mechanism, okay? I don't want to get too far outside of it, but to keep it real, for everybody, this beautiful thing called the permutation generating function is veritably the essence of what we do when we deal with statistics, when we deal with, well, just about anything that requires math. So for us, the permutation generating function, this piece of T thingy, is really a statement about general covariance. It tells you that you can switch labels on anything, and these are the sorts of ways of accounting for how labels can be switched amongst, bananas, oranges, and apples, and yet you're still able to perform a count. You're still able to get something valuable out of that system. Okay, I'm going to move on. Okay, so what we're showing here is that in a universe where we're talking about something called the number of vertices, I think of the universe as a bag of vertices. And what I'm trying to do with those vertices, or a bag of cards, or a bag of marble, it really doesn't matter, but some very finite system of stuff. And how we mark that stuff is called vertices. So one thing might be on one vertex, something else might be on another, whatever. So the idea, though, is that if we basically define that the number of vertices of our system, the number of cards in our deck is fixed, then we can begin to talk about whatever card game Vegas is about to win money from you with. Okay, so what we're establishing here is that there's a very, very elegant statement about the permutation generating function, this thing we call PT, and this other thing we were talking about called the cyclic generating function that we call GT. And again, all the cyclic generating function is a way of counting things, objects, cards, etc. And then exponentiating that gives us this other way of statistically talking about the arrangements and rearrangements of those cards, this permutation generating function. And what we find is it has a very, very elegant form, 1 over 1 minus z. Now, think about this for a second. We had one thing, this thing we call GT, the cyclic generating function, it's veritably an infinite series, or it's very big, and it's got z to the 100th power to it. But all of a sudden, if you exponentiate it, you get this very small algebraic structure, 1 over 1 plus z, or 1 over 1 minus z. This is elegant. This means that something that looked unreasonably big in size is now something that's a very simple algebraic equation. 1 over 1 minus z, you can probably do it in your head. Tell me what z is, I'll do the calculation. The point, though, is that the permutation generating function takes on a very small, tight form. And that tight form is veritably fixed. 1 over 1 plus z, or 1 over 1 minus z. It's a beautiful thing. Okay, so what we demonstrate here is that what we call Feynman propagators is directly related to this concept of a permutation generating function. In fact, we can show in this slide how you get from one to the other. What assumptions do you make to make this transformation possible? And we'll get back to this. Okay, so what do you do in terms of getting real physics out of either one of these things? So where we're going to start, which, by the way, there was a paper that we produced before on relativity theory, where we start exactly here. What we demonstrate is that when you look at those cycles, like the z squared, z cubed, this generating function, and you just split the generating function into two pieces. One of the pieces only has odd cycles, z cubed, z to the 5th, z to the 7th, etc. And the other one has even pieces, z squared, z to the 4th, etc. The thing about these two generating functions, this breaking apart of the cyclic generating function, the beauty about that is that all of these parts are always added together. You're not really breaking the generating function into two pieces. What you're really doing is choosing one part and then later adding the second part. But the point here is that physics, as we know it, the equations of physics, simply come about by how you choose to look at that cyclic generating function and just to break it into pieces. Relativity appears when you break it into two pieces, odd versus even. Quantum field theory occurs in this case when you randomly break it apart, which is bizarre. But quantum field theory is a much more basic structure than even relativity theory is. And for this reason, because when you're choosing how am I going to, am I going to look at the z and z squared part of it? Again, when I say generating function, think of a polynomial and just ask yourself the question, okay, do I want to just move some parts over here and other parts over here and then deal with them in different ways, deal with them later from each other? Or Do I want to look at the whole thing? And what we're saying is that the physics that we actually use in our world is really simply how someone has decided to break apart the cyclic generating function and to proceed to measure one part of it or proceed to look at another part of it. So what we're saying here is that formally, scattering theory, how we take a ball and throw it at the wall and then watch how it bounces off. How does the wall react to the ball? How does the ball react to the wall? That's scattering theory. And every trick about quantum mechanics comes down to that. Here, what we're saying is that all of the equations of quantum field theory simply come about because you're looking at this thing we call a cyclic generating function, and you're just dividing it into several parts according to whatever your whim is. The measuring device, the Large Hadron Collider in CERN, Fermi Labs collider, all of those colliders are just different ways of looking at the cyclic generating function and breaking it down into different pieces to measure different things. That's the whole point. Okay, so the idea is very simple here. That if you give me the cyclic generating function, you break it into two pieces. One of the pieces we're going to call an arrangement, and the other piece we're just going to call it a derangement. And they actually have special and different properties to them. We're marking the arrangement and the derangement by an A, obviously, and a D. And we're saying that, again, in the cyclic generating, you're just pulling it apart additively. But in the exponential or the permutation generating function, this thing called PT, it's really the product of those two things. But we'll get to that. Okay, and here all we're showing is that the permutation of the bullet, the thing you're throwing at the wall, is really just the exponentiation of the cyclic generating function that you pulled apart only for the arrangement. Again, the arrangement is just some way of separating some part from another part. Okay. So here's a random commercial break. Now, if you guys have any questions right now, please don't hesitate. And by the way, you can silence this part, or I'll put it on silence, whatever. But it's just a random commercial break, and I'm inviting any questions at this point because I know it's been a lot so far. I know it's a really cool animation. But are there any questions?
Well, Ken, typically we do questions at the end of
Okay.
the overall session. Now, so Jeremy Rys had said he's having trouble with your audio because of the mask.
Oh, yeah, I could just hold this thing up to my mouth.
There we go. Yeah, and I can hear you okay, but he indicated that he was having some audio issues with it.
Okay. Is this better?
I'll leave.
Huh?
Jeremy, do you want to text me and let me know?
Come on, Jeremy, let him know. Okay, so
I think that's better.
We'll wait till the end for the questions. I pray, Jeremy, that you can actually hear me through this. If not, we'll have a one-on-one.
Yeah, well, okay. Ken, I can definitely hear you okay. I think I have everybody else muted out, so
okay.
I'll put myself back on mute. And sorry for the interruption, sir.
Oh, no, please interrupt. Okay, so here, all we're saying is that when you define both the bullet in terms of a series of cyclic generating, a series of cycles on a generating function, and you equally then can define the target as the remaining cycles. We call it the Rencontres number. It's French. I don't know French. I only know Spanish. So forgive me for not pronouncing that correctly. But we call this other thing the target generating function. We have a word. We call it a derangement. Okay. So what we're able to do again is to separate out some general polynomial that we call a generating function into two pieces. One piece will serve as a bullet, and the second piece will serve as a target. The beauty about this way of doing it is that when you bring both pieces back together, you get effectively what we call the universe. And all we're really saying is that the universe is nothing more than you randomly dividing it into two pieces. I kind of think about, you know, that Michelangelo picture of Adam and God touching finger. It's kind of like that. You know, it's a whole big darn thing, but for some strange reason, you can divide it into two pieces. You and everything else. Okay. But when you do that, you have effectively created what we call scattering theory. Now, the novelty about this way of thinking about scattering theory is that the whole system is always taken into account. And the way we do that is, at least with the permutation generating function, it's simply the product of both the bullet and the target. And in the end, we get back to something we know very well, which is this 1/1 minus z, very small algebraic representation of what we call the total permutation generating function, the thing that marks all of the different ways you can relabel the structure of measurement, the structure of the universe that you're actually working with. Okay. And again, if I go too quickly through these slides, because there's a lot of reading, don't hesitate. You know, certainly read it on your own. Come back to me, or read it as I'm talking. Come back to me, however it works for you. So what we're showing here is how do you establish special relativity theory from these generating functions? It's really very easy. And we're not going to go through this explicitly here because we do that in a prior paper, but just to give you how that actually looks in this particular slide. Okay. But what's much more important to us here in scattering theory is this idea of the target versus the bullet. And in the target, in regular quantum field theory, we have an idea of how to talk about a target. How do you talk about something that you're firing your particle beam at? And the way we talk about it is we talk about it as a Yukawa potential. It is this energy domain where when you throw little electrons at it, the electrons decide, hey, you know something? I'm going to bounce off of that. So that thing that it's bouncing off of, that target, we actually have a potential energy that's associated with that target. And normally what we're trying to do in particle physics is to understand that target. You know, because supposedly we already know what our bullets are, right? We kind of know what the electrons are, whatever we're using in our particle accelerator. What we're interested in is what the heck is happening once we hit the target. What is that target? How is that target, you know, effectively described? That's what we mean by Yukawa potential. And in this description, we can always get to what is that Yukawa potential once we've begun to bombard it with our, you know, with our bullets. And here we have our actual definition of that. That's directly from the permutation generating function of the target. I mean, that makes sense, right? Okay. So here, again, we have this two-part series. We've taken the whole universe, we've chopped it in half, or chopped it into two pieces. One piece will serve as the bullet, another piece will serve as a derangement or a target or a Yukawa potential. And we're just giving you a sketch of what that means. Okay, another place for a commercial, but we're going to get past that since we're at the end with our questions. Okay, now let's be realistic. Having a two-part universe with Adam and God is veritably insufficient. There's no room for anything but God and man love. Okay, we need something more. We need to actually understand that when you actually are doing a particle experiment, you're not trying to measure the whole darn universe. You're only trying to measure something in front of you, hopefully. So we have a nice expression. We can divide the universe not into two pieces, but into three pieces. The generating function, the cyclic generating function that we started with, enables you to divide the universe into any number of pieces. So we're really choosing here to ask, well, what happens if we choose to divide the universe in three things? You, the measurer, whatever you're trying to measure, maybe it's the microphone, and by the way, and everything else. Okay, so I'm looking at you, Tim, you're in the background. So I can't, I'm not watching you. I don't know what you're about to do next, but I somehow know that whatever you're going to do is probably going to affect me and this microphone, such that I have to take you into account to be a realistic experiment. So here's to you, Tim. But the idea here is that if you, instead of being naive about how do I divide the universe between me and something else, I really have to divide the universe in 3 ways. That is our most basic understanding of experiment. You, the measurer, something that you're measuring, and the rest of the universe. So we have a tripart division of our understanding that we can do. We can do that using this cyclic representation of the universe. So we go ahead, we do it, and this is what we get. It's unbelievable. Actually, what we get is something that was already very well talked about by 2 physicists. The main one for me is Max Tegmark, because he's been talking about this for at least 10 years now. That when you choose to make a measurement in the universe, there are things about that the quantum world requires of you. And one of those things is, what do we mean by 2 systems in the universe, you and the system you're measuring, being entangled? What does it mean when the system in you become disentangled? What do we call any of it? What the heck is measurement? So Max Tegmark and this other fellow, Mr. I can't pronounce his name, I apologize. I'm just, okay, so the idea here is you've got a trinary system, a trinary representation of the universe, where you have a subject, the experimenter, the experimental device, you have an object, which is effectively what you're trying to measure, and then you have all this background noise that we call an environment. And this trinary operation is fully what we are doing when we are taking this cyclic generating function and dividing it into 3 pieces. And again, I encourage you to go back to this material and to look at my notes, look at my references, and begin to see the logic in all of this. And here we're walking through and basically saying, however you choose to set up your experiment, some part of your experiment will serve as the bullets, and then another part of your experiment will serve as the target. And this is a nice, beautiful, sophisticated way of accounting for all measurements that can ever be taken in a world governed by math. Inevitably, that's what we're trying to do. We're trying this down into the most basic type of math that deals with measurement. And again, that's combinatorics. Because all we're doing is counting structures. That's all these generating functions are doing. Okay, so here, I just wanted to make a note that a really huge breakthrough in our work here was to demonstrate that how we talk about measurement is really counting these patterns, and the count of those patterns is really these generating functions and their coefficients. So there's going to have a z squared, z cubed, whatever the generating function looks like, but it's going to be a number in front of each one of those things. And that count in front of this polynomial, in front of each one of the variables in that polynomial, is the measurement. That's what we're measuring. So what we're going to show you in this next graphic, in this table, is how do you make that association. So for example, if our coefficients of our generating function are 1 and then all the other coefficients are 0, so basically what the generating function looks like is just z. That's all it is, just the variable z. Then we account for that as the speed. Yours, what we call the relativistic speed, but it's your speed divided by the speed of light. It's a ratio. But that's what that thing is. If you get that count says you just measured the speed of the object. However, if you get another count where instead of there just being, a 1 zeros, it's all ones, what you've actually measured is what we call the momentum of the particle. And then again, if you get the 1 minus 1, etc. So we walk through to demonstrate how the generating function produces a valid, measurable thing. And in this case, it looks like relativity theory is being measured. Now, in this second table, what we want to account for is what we would call the momentum, what we would call the forces, and what we would call higher order derivatives of the forces. But in general, we call these sequences, which are really derivatives. And so the idea is that however we, or whatever we're measuring, has an associated look to a generating function involved. That look can be, again, relativistic, that look can be quantum mechanical, that look can involve things that change. For example, in our first, in this particular slide, slide 27, we see that the numbers are increasing by 1. That's a momentum. We see in the second row that or rather the third row that the numbers are increasing by 1, and then 2, and then 3, and then 4, and then 5. We call that an acceleration or a force, etc. So how things change is also encoded in this way of dealing with generating functions. And as a sort of a nice little version of that, we can recover what has generally been called the Hawking-Hartle wave function for describing the whole universe. So Stephen Hawking and another fellow named Hartle developed a beautiful way of understanding the Big Bang that was completely consistent with quantum mechanics. And in that description, I'm certain they realized that they were utilizing Bernoulli numbers in order to accomplish, how can something really just always be there and then explode into existence and then collapse and explode and collapse, etc. But that's embodied in this particular wave function description of the universe. Okay. So another aspect is that when we ask, well, if you're dealing with particles, then you're not simply dealing with zeros and ones and twos and threes. You're dealing with other measurable things about particles, like the mass of a particle, or the charge of a particle, or the spin of a particle. Basically everything that we actually measure about particles, short of their momentum, and short of the forces acting on them, involve all of these internal things, like, okay, what is the spin of a particle and why? Well, the beauty about this way of dealing with measurement is that the cyclic generating function enables us to include other ways of marking systems, we call it. And those other ways we call charges. So in PhOENIX and in most of the particle physics world, a charge is any conserved quantity associated with a particle. And in particular, they tend to be internally conserved quantities, like charge, like electric charge, like the mass of the particle, like the spin of a particle. All the things that I just mentioned are basically internal conserved quantities. And in combinatorics, the language that we're using here, those things are accounted for by something we call marking your univariate cyclic generating function. Our mark of that is that there's another property we're calling u sub I. Okay. Now, formally, when you mark your system, all of the generating functions all evolve. They become a little bit different. They all have a new mass marker to them, or a charge marker, whichever label you choose to use. And how PhOENIX defines that marker is given by a wonderful concept that in a later talk we'll get definitely in. So when we give a talk, if you guys will invite me back, when we give a talk on general relativity theory and quantum mechanics or quantum gravity, then we'll talk very much about why this definition of a marker, of a mass, of a charge, is so relevant to every part of physics that we know, because it is what is intimately involved in defining quantum gravity. But here, all we're saying is that if you don't know, the trace, this TR0, is really where you take a matrix and you just add the diagonal together. That's what we mean by trace. So in quantum mechanics in particular, the trace is used as a measurable. So when we say, well, you know, what's the momentum of a particle? Well, inevitably, we're going to go through and find the trace of some system of matrices. So here, explicitly, the trace of your matrix associated with your particle. That's what that is. The trace of your matrix becomes a marker to the charge, the mass, a property of that system of graphs. So we're not going to work on an example here, but I can sort of have a whiteboard here to give you an example if you're interested in really specifically what that means. But it is how we describe mass. It is how we describe charge. It is how we describe spin. All of those things that we talk about when we talk about systems of particles. Okay, so I am going to come to this slide. Now, what's so important about this slide is that we've been describing particles, okay? We've talked a little bit about the cycles that, you know, systems of particles have, graphs in particular have, etc. The question in how we do physics is not so much the particles, it's about what we call quantum fields. And the question is, in PhOENIX, what's the relationship between, let's say, a proton and our graph of a proton, and then the proton field that we seem to measure in the laboratory? And this is the association right here. It simply says that you do what we call a Heisenberg trick on what you're calling a discrete particle, like a proton. And then you can make that simple chunky particle into a continuous field. It's a way of saying, look, I have an ear of corn and I want to describe a corn field. So in math, we have a way for doing that. Okay, you give me the corn, I'll give you a cornfield. It's a beautiful way of Jesus multiplying fish and bread. But nevertheless, it's also a nice way of saying, how do you get liquid water from an atom of H2O, rather a molecule? How do you get that description of water that we know on the macroscopic level? So this particular transformation is the combinatoric way of taking a chunky version of matter and turning it into its continuous field version. And that's, I mean, I can't tell you how important that is. Okay. So what we realized in this exposition is that the technique, the method that we use in order to figure out what the heck we're measuring when systems are changing. And if you go back to the table I was showing you between discrete numbers and then how systems can change, what we have is that our mechanism for describing how systems actually change is known as the commutator. Now this object is given by the square bracket, two things inside separated by a comma, and then the rest of the square bracket. But all that means, if you're not familiar with commutators in math, it just means that Z and G are two matrices, and the square bracket, comma, the other one is really Z times G minus G times Z. It's really a simple way of talking about, do those two matrices commute? So if I take the product in one order and I subtract from it the product of two matrices in the opposite order, if it's equal to 0, then those two matrices commute, like regular numbers would. But if it's not equal to 0, they don't commute, and then you have a whole system that makes quantum mechanics what quantum mechanics is, because its commutators don't usually commute when you have two systems that you're trying to measure that are not compatible for measurement together. Okay. Now, so this thing that's called the extraction operator, it's what combinatorics uses in order to, when you ask the question, what is this thing counting? What is this generating function actually counting? Normally we would say, well, use the extraction operator on the generating function. It will extract out the count, okay? And all that is what is the number in front of Z, Z squared, Z cubed? Your polynomial has some numbers in front of the variables. The extraction operator just gets the numbers. That's all it's doing. It's just looking for coefficients. And by the way, those coefficients are what we call measurements. That's the important part here. Okay. So the thing that allows us to really place all of this stuff that I've just said in the context of physics comes about because we can also define calculus. Now, I don't know how many of you people were ever happy with calculus. I hope most of you were. But nevertheless, calculus is, you know, sort of how we can describe changing systems. And so it's really important in terms of everything that we're doing here as well. Now, we weren't the first one to come up with how do we use everything we've been talking about in terms of developing calculus. The first person to do that I'm aware of was Sir Isaac Newton, believe it or not. Sir Isaac Newton was 400 years ahead of the game, and obviously he didn't know it. But his derivation of calculus is entirely dependent upon a commutator methodology as well, what we call finite differences. But he developed it, and because of that, he developed calculus first. Okay, maybe Leibniz did, but nevertheless. So the idea is we come to a particular mathematician or physicist named Louis Kaufmann, who about 2004, I discovered his work and realized that he and I were speaking the same game. Now, in my work, I expressed a lot of the stuff that I just expressed to you, but I had this evolution equation, which you see in blue in the center of the screen. The evolution equation is very simple. It says that if you give me a graph, this equation will tell me what that graph, oh, by the way, the graph is a particle. It is a graphical representation of a particle, like a proton or a neutron or some other system of particles. But if you give me the graph, the matrix of that graph, then I can determine with that equation alone what that particle can become and also what it cannot become. So this is what we call the evolution of our evolution equation, the evolution of graphs into new forms. And this is how effectively Kaufmann also starts his paper. He demonstrates that this particular evolution equation that we both share actually is the essence of what we call commutator calculus, in particular commutator derivative calculus. And I invite you guys to really read through the slide. But there are two parts. There's the graph that we have given the name chi, or x if people don't know Latin. And then the thing that changes chi, which is called T, the transformation matrix. And these two matrices, again, have this wonderful property to them. We call it a similarity equation. But these two matrices enable for chi to become another type of chi. Okay. And the expression at the bottom here is exactly that. Now, Kaufmann goes into a lot more finesse and detail in terms of, what's really happening here quantum mechanically with these matrices doing the dance that they're doing. But we are very happy to simply reside in the idea that one of the matrices represents particles and space and a graph, and the other, the T matrix, represents a transformation or time. And again, what Kaufmann is doing in particular is walking through how this association between these graphs and this time, these transformations, yields quantum mechanics. And in particular here, we're able to yield Heisenberg's version of quantum mechanics, where we come up with our evolution equation, etc. Now, what Kaufmann really does that is still beautiful to me in so many ways is that he's able to show, and we walk through it here, we're just not going to go through it because I'm sure I'm putting half of you to sleep, but we're able to show, he's able to show, that there's a way of defining a derivative and three different types of derivatives that are associated with these commutators and are associated with our our matrix chi and our transformation matrix T, to the point where he's able to define a singular type of quantity in special and rather general relativity theory called the metric. And that metric, this Gij, is actually associated with the commutator of space and momentum. Now, if you guys remember about general quantum mechanics, that these two concepts, space, measuring something spatially, and measuring something in terms of its momentum, are not commuting variables. Okay, effectively what it means is that if I measure something about space, and then I want to simultaneously measure a particle's position in space rather, and then simultaneously measure the particle's momentum, its speed, I can't measure both of those quantities with arbitrary accuracy at the same time. Because if I measure one very well, the other one gets thrown off. So that's given to us by this commutator relationship. But what Kaufman is saying is that that same commutator relationship describes something called the metric. It's describing a way of defining how things are even measurable in the first place. And that's big, that's huge, because that Gij is what is the basic tool of Einstein's general theory of relativity. And it comes out of this commutator relationship that Kaufman is able to demonstrate. I'm going to skip through that one. Now, and we're going to skip through this commercial since we've got questions at the end. Okay, so what do we do in PhOENIX? We generalize Kaufman's work on derivatives. We give it a much more basic understanding. I mean, he does a really good job. Please don't get me wrong, the man is a genius. We just take it to a level where we can apply it to any system, any matrix system, not just matrices that are somehow dealing with a particle. This applies to all matrices. That's the beauty about this. So if you've got a system described by matrices and you want to ask, well, what's the momentum of that matrix? This is the stuff that will get you that answer. If you want to know the physics of a database, I don't care what the database is. The database is described by a matrix or a series of matrices. This math works for it. And you will have a physics way of looking at your data. It's beautiful. Okay. So we generalize Kaufman's derivatives, and we have a reason for that, because we'll get to that in the last section. But the reason is because Kaufman never came up with integrals. It's wonderful to have derivatives. I grant you that. Calculus is beautiful with it. But you have to be able to undo derivatives, right? I want to know the whole circle, not just a slice of it. So if you want to get the whole circle, you need integrals. So we were able to give Kaufman the integrals that he never knew he had. Okay. But nevertheless, here, what we're talking about is that when we are dealing with these commutator derivatives, we're also dealing with two things. We're dealing with matrices, which are describing sort of like chunky look at particles. And then we're dealing with another type of variable, a scalar variable, that's really associated with a continuous way of looking at our particles. So one is a particle version, the matrix operator, and another one is a field version, or the scalar variable, the scalar operator, if you want to call it that. One of them is describing the wheat, the ear of corn, and the other one is describing the field of corn. One of them is describing the chunky energy associated with a water molecule, and the other one is describing how waves of water crash on the shore. Very different descriptions, right? But these are the descriptions that we utilize, obviously. One of them is fundamentally quantum mechanical, and the other one is fundamentally thermodynamic. Okay, and that's a really important distinction, but that distinction is incorporated in his derivatives. So we can always maneuver between chunky, microscopic reality and the reality that we seem to live on, which is a reality of fields permeating all of space. Okay. So we're going to walk through this, meaning that we're not going to talk about it as much. I'm going to skip ahead to the integrals. But Take your time in going through this. You're going to be astounded. By the way, the reason why we like commutators is because they're easy to do. When was the last time you really worked through dealing with derivatives? I mean, you know, it's tough. You got a lot of things to memorize. Here, you don't have to memorize a lot. Okay, so one of our main achievements in PhOENIX is coming up with an integral version of what the heck Kaufman was just talking about with derivatives. And although we were able to recognize what this was in terms of Kaufman's derivatives, we were actually beat to the punch by that same guy who I love to hate and hate to love, Werner Heisenberg. Thank you, Werner. Okay, so what Werner did when he came up with his Heisenberg representation of quantum mechanics is he figured out a nice little math trick. And this math trick is governed by this exponential of b and times a times the exponential of minus b, etc. But it's a math trick that allows you to start talking about commutators upon commutators upon commutators. And what we were just talking about is that commutators represented derivatives. Here, we've got all these various, you know, Russian doll versions of commutators all added together that is speaking directly about derivatives, because that's what they are. But, you know, Heisenberg, I don't think really realized it in that context, because honestly speaking, it was Kaufman, you know, 40 years later, who really did put it together in the context of derivatives. So now we can utilize both of those to understand how to undo what Kaufman was doing, how to take derivatives and to integrate with them. And that's what we're showing here, that effectively this subtle trick that Werner Heisenberg came up with is really explicitly what we call integration. And the integration is of these little derivative pieces that Kaufman was talking about. Okay. So what we do here is, actually, let me go back one slide, I apologize. What we do here is we show that if you give me a graph, like a graph representing a proton, I'm going to call that A sub alpha, or A sub A rather. You give me that graph, and then you give me a transformation that will take, let's say, that graph and turn it into another graph. We'll call that B. Okay, that transformation we're just going to call B. And you stick it in this and you utilize all of these commutators. What you've actually done is you've integrated that particle, whatever that original graph was, you've turned that ear of corn into a field of corn. The description of the field is this A, and then in parentheses, a function of a scalar parameter or scalar, or a continuous variable, B. That is your field of corn coming out of your ear of corn. So, you know, I wish farmers would tune in, right? Because if they did, they could probably judge their whole corn crop. Because you just perform this little integration and you get the whole darn thing for the season, okay? That's pretty good. But what's good for us is that you can turn a water molecule into an ocean of water. You can turn something that is inherently quantum mechanical into, in point of fact, what we observe, you know, a cup of water. Or in one more analogy, you can turn binary language, which is the chunky stuff, the A sub alpha, or A sub A rather, you can turn binary language into Microsoft Word. Okay, so it might not work out so well for you that way, but effectively what you've done is to turn chunky objects into continuous form, into field objects. Okay. Now here what we do is to demonstrate that the Hamiltonian that we're associating with quantum mechanical systems can actually be derived directly from everything that we've been talking about. And we're gonna skip through this, but okay, so this is one of the big kicks about everything that I've been saying. If you give me one of our particles, like a proton, and I turn that into a matrix, like this chi sub I here, I can then use this commutator stuff in order to turn that chunky proton into a proton field. And in particular, the field of the proton we're talking about is its spatial arrangement in space, this X or chi sub I of t, is its spatial arrangement, okay? How does it smooth itself out in space, or how does it re-chunkify itself according to a continuous time variable? But we didn't have to do anything more than integrate. So what we did here was to perform that integration. And the way that integration actually looks is an extension of what we would call Newton's second law. So you see, there's a location, namely chi sub I. There is a momentum, rho sub j, and then there's a force, F sub k. Those are the chunky things that we would normally associate with your initial position, your initial momentum, and the initial forces acting on the system. So Newton's second law. The way it's written here is so that it will give you how does that particle move through space. The space we're dealing with is the space you see right around you. And the time, how it's, what time is it using to move? That's a continuous parameter as well. So this has turned your corn, your ear of corn, into your field of corn. And you can track how is the corn moving as a wave through the system. That's what the X sub I on the left-hand side represents. It represents a continuous macroscopic way of seeing the particle system. And then the particle system, the chunky particle system, is really represented on the right-hand side of the equation, with where is it, how fast is it moving, and what are the chunky forces acting on it. So in other words, we recovered Newton's laws. We'll get to gravity, Newton's third law, in the next lecture, if I'm invited back. It's a random commercial again. Okay. So really, that's what I have. All of this stuff that remains here is really about going into greater detail about how to perform integration. And I'm always asking myself this question: are we done yet? Are we ever done? No, this keeps going. On and on and on. Do you know how much physics there is to show it? Okay, so you get it. But what we can say is that everything that we've just demonstrated here, the reason why I'm walking you through it like this is because you won't be able to understand what I'm going to tell you about quantum gravity if you don't understand this. And that's the power here. The power here is that when we do talk about quantum gravity, then we have a very easy way of understanding how to manipulate it. Because we understand what quantum gravity is at the subatomic level, at the most basic level of particles that we currently do not have except for string theory and loop quantum gravity. And inevitably, when we do introduce quantum gravity, we'll go through what parts of string theory actually are correct and what parts of loop quantum gravity actually are correct. It's nice to know that there's some good parts in both of them that actually come out of our version of quantum gravity. So yeah, I mean, if you guys have any comments, questions, or criticisms, please let them roll like the waves.
Well, so Ken, I think that means we should probably move into our Q&A session then, right?
Yes.
Okay, yes. Before we do that though, let me stop your screen share.
Okay.
And so I want to put this on, sorry about that. Okay, I'll stop the screen share there, and I will put this on gallery view. I hit the wrong button. And everyone, please give Mr. Kenneth Griggs an enormous hand for a tremendous presentation. That was a full hour of super intense math. So thank you, sir. Thank you very much.
I'm sorry.
Oh, no. It's wonderful. That's wonderful material.